Okay, this topic is called KSP, and you'll see it ties us back to the beginning of the equilibrium unit where we were working with Kc. When you did Kc, this C stood for concentration, which meant we were just, as long as we were plugging in molarities, we were good. It was products over reactants. We excluded solids and liquids, pure liquids. Coefficients became exponents. All of that. Still true. KSP has the same rules. Products over reactants, coefficients become exponents, exclude solids and liquids. The SP stands for solubility. Product. We're still using concentrations, but SP is just giving us a heads up that we are working with insoluble compounds. Insoluble, like not soluble. At least that's what you probably think insoluble means. Really, what insoluble means is that we are dealing with barely soluble salts. Compounds. Things that, as far as we can tell, don't really dissolve, but actually a teeny bit of them does. So when we're dealing with KSP, if the problem talks about KSP at all, we know we're dealing with something insoluble. And so let's say it was this salt. We know it starts as a solid because we're going to dissolve solids. So it always is starting as a solid. And you're used to breaking it up into its ions, a positive ion and a negative ion. Only two pieces. If it's a polyatomic, it would all stick together, and no diatomics. So that's what you're used to. However, because it's a solid, because it's insoluble, which we'll know it's insoluble anytime we're talking about KSP, we use equilibrium arrows for the dissociation. Because it's not really dissolving, it ends up being a system more in equilibrium. Anything that does dissolve is likely to stick back together and reform. There's a heavy leaning towards the reactant side in these reactions. So we're always dissolving solids using equilibrium arrows if it talks about KSP. I will show you that in all of the example problems we do, but that is where you want to start. Dissociating, equilibrium arrows, two ions, that's it. Okay, so through one giant problem, I'm going to teach you everything you need for KSP without actually reading parts A, B, C, or D. As soon as I have the salt that we're working with, there are three things I can always do. One of them is write out its dissociation. So AlOH3, which is a solid. We're always starting with a solid. Equilibrium arrows, because you can assume that I'm giving you something at equilibrium in this unit. It's going to split into aluminum, which is a +3, and hydroxide, which is a -1. So that's one of the things I can always do. Write out my equation. The next thing I can always do is an ice chart. Now, these are going to be the easiest ice charts you've ever done because they follow a pattern. Ultimately, we know we're dealing with KSP. So we know we're going to be plugging into products over reactants. Our reactant is always a solid, and solids don't belong in KSP expressions. So when I go to write actually, I'm going to pause on the ice chart. I can go write my KSP expression, my products over reactants. My reactants, a solid, aren't going to get plugged in, so I just put a 1 there. Always, every time for KSP problems. My products, it would help if I had balanced the reaction. 1 aluminum, I need a 3 in front of my hydroxides. So this is cute. So that's my KSP expression. You do not have to write the denominator if you don't want to. But we're never going to plug anything in there because it's a solid. So when I do my ice chart, I don't need to fill that out at all. It's not worthwhile. It's not going to get plugged in anywhere. Now, I didn't even give you any numbers, my products are always going to start at 0. Because we're always taking this solid and attempting to dissolve a little bit of it, so I don't have any of the ions before I've dissolved it. Since they're zeros, it's always plus on this side, which gives me x and 3x, and I can go plug those in. However, and I'm sorry if you wrote in pen, when I'm doing KSP problems, instead of x, I use the letter S. Nothing actually changes, but I do that for a reason. You'll notice one of the things they ask us to find is molar solubility. To remind myself of that, S is my molar solubility. So by using the letter S, it helps me realize that. If you want to use X, that's no problem. I just use S. So again, I haven't read the question whatsoever, but I'm able to write the reaction, fill out my ice chart, write my KSP expression, and I can even plug the equilibrium values in. Aluminum has a value of S, hydroxide is 3S, and it's cubed. And I haven't put anything here, I'll come back to it. I can simplify this. So 3 cubed, 3 times 3 is 9, times 3 is 27. S cubed times another S gets me S to the 4th. All that work just from knowing what salt it is. Now, KSP values, there's a chart for, but it's on my website under tables and charts. When I pull that up, I'll see that there's a value for aluminum hydroxide on the chart. So you probably want to pause here, open up another tab, and go get that chart. I look for aluminum hydroxide, and I find a value of 1.8 times 10 to the negative 33. That chart, if you look at the top, says solubility products. So KSP is solubility product. That's why I can plug that value in as my KSP. Now I want to solve for S by itself. So first I divide by 27. Hold on. 1.8 times 10 to the negative 33 divided by 27. I get like 6.67 times 10 to the negative 35. That's S to the 4th. Now, if this were squared, it would be easy. I would square root both sides. If it's any number other than squared, what I'm going to do is take this number in parentheses and raise it to the 1 divided by whatever that number is, in this case 4 power. So if it's S to the 4th, I'm raising it to the 1/4 power. The parentheses around the 1 divided by 4 is really important on most calculators. If at this point you get like 0.000003, you want to put your calculator into scientific notation mode. So on the calculators that we use in class, I would press second and the button just to the right of second, and I would go over to Sci and press enter. That helps me see that my S value is 2.86 times 10 to the negative 9. If you want to get out of scientific notation, second, that same button just to the right of the second button, go back over to flow and press enter. If you're having calculator trouble, pop in and ask a question. If we need to make a video showing you different types of calculators, we can try to do that too. Whew. Okay, so I just did all that work. That S value is my answer to A. Molar solubility always means find the S value. At this point, you might want to pause and go, actually no, let me keep going. But if you need to go back and re-watch that to make it make sense, go for it. Okay, we've actually done most of the hard work. So, answer to A, 2.86 or something close to that times 10 to the negative 9. For B, find the concentration of OH. Well, I imply that I mean at equilibrium. That is the value of OH at equilibrium. It says 3 times S. So for part B, I take 3 times my S value. And that's my answer for B, and that's it. I'm going to make sure I stay in scientific notation mode just to make my answers not be rounded. Like, your calculator will crazy round them for you. It'll truncate it, essentially, when the numbers are this small. So I get 8.57 times 10 to the negative 9th. And it's brackets that tells me its molarity. Molar solubility, this S value, our ice charge, all of that, like they have been all unit, are also in molarity. Okay, so for C, my molar solubility is basically saying how many moles of aluminum hydroxide can I get to dissolve in 1 liter of water. It is my solubility in moles per liter. 2.86 times 10 to the negative 9th is molarity, or is moles per liter. And what they want me to find is the solubility in grams per liter. So really, I'm trying to take this number that's in moles per liter and just get it to be in grams per liter. Erase this so I have more space. Now, different people like looking at this different ways, but essentially, the per liter part isn't changing. So I just like to think about, I'm trying to go from moles to grams. How do I do that? Multiply by molecular weight. That's it. So I'm going to take for part C, I don't want to get cut off here. I'm going to take my S value, that's in moles per liter, and I'm going to multiply by the molecular weight of aluminum hydroxide. So, oops, do I not have the answers here? I do not. Aluminum's 27 plus 16 times 3 plus another 3 gets me a molecular weight of 71. If you're still in scientific notation at this point, it might say 7.8 times 10 to the 1, which is fine, or you can take it out of scientific notation. Times 2.86 times 10 to the negative 9th. And I get 2.23 times 10 to the negative 7th grams per liter. Units matter a lot here. So my answer for C, 2.23 times 10 to the negative 7th, basically means I can get 0.000002 grams of aluminum hydroxide to dissolve in 1 liter of water, which is barely anything, which is like not a lot, which is why we say that this compound is insoluble, because as far as our eyes can see, it's not dissolving. But that would be it in grams per liter. Your units matter a lot here. Going from moles to grams, we multiply by molecular weight. In other problems, you'll see on all the try problems, I ask you to find different things starting from different places. Going backwards from grams to moles, we would divide by molecular weight, and it's always of the salt. Okay, we need this answer then to do part D, which is how many grams of aluminum hydroxide can dissolve in 15 liters. Well, I just learned that 2.23 times 10 to the negative 7th grams can dissolve in 1 liter. That's what this number means. I want to find how many grams can dissolve in 15 liters. A lot of people see other ways to do this. If you want to just know to multiply this by the number of liters, you may do that. But again, depending on the information you're given, grams per 1 liter, grams per some other number of liters works as well. Cross multiply, and I get, cool, let's knock it off. 3.35 times 10 to the negative 6th grams. So, that was one long video showing you everything I could possibly show you. For the try problems, there are a bunch of them, they're not all this long, and they give you different information. This is how I normally do this lesson, even if we were in class. I show you everything, and then I ask you to work together to figure out the try problems. And I come around and help. So you might have more questions today. You might need to rewatch parts of this video. Know that as long as you always start with the reaction, the ice chart, setting it equal to the number on the KSP chart, and solving for S, that's generally a good way of going about things. Good luck. Try. Don't give up.